Science has misunderstood the water molecule now going on, well, pretty much from origination. They never quite did figure out what's going on there. And I'm sorry to say that I think a lot of the misunderstanding is systematic. In other words, they are locked into kind of a belief system which prevents them from seeing that the solutions to this are pretty straightforward and pretty simple. And it mostly starts with making sure you understand what's going on with hydrogen bonding. That's the biggest difference between my approach to things and the approach that's been traditional. They've talked about H2O polarity. They described it well. We have an understanding of what it does to the electrons on the H2O molecule. And we understand the dynamics of it. But we made a mistake at this point. This is where we thought we kind of maybe got a little bit overconfident. We just assumed that any external effects of the H2O molecule wouldn't have an effect on that polarity. Another way to say this is that we assumed that polarity was like a lot of the other forms of attraction that happen on the molecular basis, you know, covalent or ionic. Ionic being the most pertinent one, because ionic is a pretty straightforward attraction. You have one molecule that's relatively negative, the other one that's relatively positive. Maybe there's electron charge, maybe not, but whatever the case, you have this charge that increases as the molecules come together, and it stays maximum. It's a constant connection. Now, what I'm saying is when we actually understand what's going on with the H2O molecule, we understand it as polar. We have to understand that polarity is different than the mechanism associated with the ionic bond. It isn't just a sharp difference in charge. It's a difference in charge that has to do with where the electrons are located. And here's the big part: the electrons don't necessarily stay still. They actually change as a bond is formed. And that means, unlike how ionic bond is, charge gets stronger as you get closer, with a H2O bond or a hydrogen bond, something very different happens. As the charge is completed, the force that's completing them gets smaller. And it has to do with this one aspect of H2O polarity that I think everybody missed, and that has to do with the importance of symmetry and the realization that hydrogen bonds actually complete symmetry. You see, for a model to be a polar molecule, it has to both have electronegativity differences in its covalently bonded molecules, and here's the big part, and the arrangement of those things have to be asymmetric. Means they have to be lopsided in some way. And that's what's going on with the H2O molecule. That's what its polarity is. But what people don't realize, though, is when you complete hydrogen bonds, you complete the symmetry. You complete that four-sided corners of the symmetry, just as if you were creating a covalent bond. And so what you've done is you've neutralized the polarity as you complete the bonds, and it sets up a strange kind of relationship on a molecular level. It's an inverse relationship. It's where the closer the two, one being hydrogen, the other one being oxygen, the closer they get together, the more the charge that pulls them together is neutralized. And thus, an H2O molecule that forms two hydrogen bonds with two other water molecules will have its charge literally reduced to zero. You know, one will be on one of the rabbit ears, one will be on the other of the rabbit ears of where the bonded pairs are on the oxygen molecule. But that, just as if it was a covalent bond, that relationship neutralizes the polarity. So that's why water is, when it's in a liquid state, that's the state that results from the fact that there's very low charge existing once they are bonded. Kind of an ironic little bond, because it's only a bond when they pull away. When they are fully bonded, it's not really a bond anymore. And so H2O can be thought of as kind of like a gas, but that maintains close proximity to each other like a liquid. But under normal conditions, a little bit of kinetic energy and they start to pull apart again. So it's almost like it's trying to be a gas, and just as it starts to do that, the charge returns and it pulls it back again. And so you had this pendulumic relationship going on there. And as you can see, that pendulum relationship literally stores energy also. In other words, as the energy, kinetic energy hits one, it goes out here, charge returns, brings it back again. You don't have that relationship anywhere else in nature. You only have that relationship when you have a polar molecule that can be neutralized by its own hydrogen bonding, as we do with water. And that's a big reason why water is so unique. And that's a big one too, by the way. That is water's high heat capacity. That's the mechanism. It's that inverse relationship happening on the molecular level. And keep in mind, hydrogen bond is very different than ionic bond in that respect. In ionic bond, molecules come together and that force stays. In the hydrogen bond, molecules come together and the force disappears and they hit against each other and they bounce away again. See that? Kind of a pendulum. There's energy being stored in every one of those swings of the pendulum, and that's why one of the main reasons why water is so important to so many aspects of nature, where temperature regulation or energy regulation or life for that matter, why our whole planet, which is 70% water, stays at such a relatively constant temperature despite the atmospheric, what's going on up there with the outside of our atmosphere. So these are big pieces of the puzzle.